Great. Hi, everyone. It's 4 p.m., so I'm going to get started here. So good afternoon, and thank you for joining this short talk. My name is Danielle Heymann, and I'm a data scientist at NIH, NICHD, the National Institute of Child Health and Human Development. And I am part of our referral and program analysis branch, which I'll refer to as RPAB. And I'll say it out a few times because we have a lot of acronyms. And today I'll be discussing how generative AI can be integrated into classical decision sciences at NIH, NICHD, showcasing some innovative methods and highlighting our NICHD RPAB AI ML grants application referral system prototype. I'd also like to start by acknowledging my colleagues, Dr. Sharon Law and Dr. Nancy Zoe, whose contributions have been instrumental in developing the work that I'll be presenting today. So here's a brief overview of what we'll cover today. We'll begin with an introduction to generative AI beyond chatbots, move into specific applications like topic modeling and predictive analytics in action with the RPAB AI ML project, and conclude with an enhanced classification algorithm and some discussion. So I hope that by the end of this presentation, you'll learn about some of our NICHD RPAB efforts and how we're striving to streamline our processes with AI ML, and that you'll also have more methods in your toolbox of using Gen AI agents in your own organization's models and systems. So generative AI, particularly large language models, have transformed how we interact with information, but their true potential really extends beyond chatbots. And in decision sciences and analytics, these agents can go beyond answering questions. They can process data, predict trends, and develop into sophisticated analytical engines. And this evolution is really key to advancing our capabilities in handling complex data and also improving decision-making processes. AI agents are crucial in modern analytics for several reasons. They can dissect very complex data and reveal underlying patterns in data that we have, and also forecast future scenarios. These agents can transform language into logic and scale our ability to interpret vast data sets, and also handle challenging edge cases that we may have in our own use cases. So additionally, they provide essential review and quality assurance, which we'll speak to towards the end of this presentation, and ensure the accuracy and reliability of our models and analyses. So traditional analytics have several bottlenecks, and one is that we all are familiar with is just being overwhelmed by the volume of data and the required pre-processing that comes along with it. Anaconda and Coursera have done surveys that they've seen that in the data science fields, data scientists spend about 35 to 45% of their time just data wrangling and cleaning. So that's a lot of time, and I could vouch for this myself. And with generative AI, we can streamline data handling, enhance speed and efficiency. So it goes deeper into data interpretation to uncover more challenging patterns and discoveries. And with AI agents, they can dynamically adapt to new or changing data and address the inflexibility of some of these conventional methods that we're used to. And they could also accelerate processing time and conduct quality assurance for us, and significantly improve the traditional analytics pipeline. So the first theme area that I'll start with will be a small case with topic modeling. So I'll be using NIH Reporter data for the use case here, and that is NIH Reporter data are funded research projects, so it's all publicly available. And we can uncover hidden themes with the data and generate coherent and descriptive labels for each theme with Gen AI infused to the the regular LDA models. So this process involves NLP methods to identify patterns and insights in data, and we can enhance the process and provide clear and meaningful labels that are quite specific to otherwise unlabeled clusters. So this is the first of 3 sections of this presentation that's focused on like method and use case. So LDA identifies, and LDA is a topic modeling method, and it identifies themes and clusters the data, but doesn't provide explicit labels. So it makes it pretty difficult to interpret the results because we don't have a label generated for those clusters. We're just left with clusters, which is great, but a human typically will go in, or there are different heuristics that you could create to generate labels. But with LLMs, we can quickly enhance this model and have generative AI agents to produce meaningful labels for the identified clusters, adding missing context and clarity. So this slide shows how a generative AI agent can transform traditional LDA results into actionable insights and improve the interpretability of the data. And this framework illustrates how you can integrate LLMs to like a typical LDA workflow. I also went with this example too, and this kind of method, because if your agency is just, or your agency or organization or company, if you're just adapting to AI and generative AI, it's really important to start with like low-risk use cases. So for here, it's a descriptive analysis of documents, and there's a lot of like human review and checking, and it's a fairly low-risk, easy to assess method, I think. So it's also why I went with this. So back to the tech stack here, you have the typical LDA topic modeling, data ingestion, pre-processing, create the model, and then we have the generative AI agent for label generation. So for the demo that I'll show, I provided the agent with context of the abstracts and the titles and the research aims of all the projects from the NIH reporter data that I sent to it, that I provided it with. And it was able to take that context and produce meaningful labels. Different cases will require, and different models will require different like engineering methods to address memory and compute challenges. So there are a few ways to do that, and ultimately you're left with the labels, the clusters with labels. So here's a quick demo, and we'll see how the LDA model and generative AI combination can address this issue. And again, very low risk use case, especially for federal agencies that we navigate a lot of AI, Gen AI policies right now, so it's really important to start with simple steps here. So moving on to the demo, I provided it with research projects from my institute, so NICHD, Child Health and Human Development. And we see pretty specific labels that were created by the agent. So going back, okay, sorry, I have to start over. In the beginning, you just see the numbers for the cluster ID, and then you have more specific labels that are generated by the agent. So things like endometrial repair mechanisms, embryonic development, and genetic regulations, those are pretty specific labels, And I had my team of SMEs review this, and they were quite impressed with the results. And next, I will discuss our NICHD RPAB, so Referral and Program Analysis Branch, our classification model prototype, and this is for streamlining our grant application process, which is typically a very manual process because we get many grant applications every year, and it takes a lot of human review to properly route those applications to get them in front of the right eyes. So this project addresses that, and I will go more into depth of the use case and where we're at. So we'll take a closer look at how grant applications are referred within NICHD. First, a stream of applications flow into our ecosystem, and each application represents a unique research project. These applications then have to go through a very meticulous review that's led by our RPAB SMEs, who are experts in different scientific areas, and they navigate through a multi-stage referral funnel. This starts at the IC level, so institute or center level. At NIH, there are 27 ICs, or institutes. Progresses into the branch level, and then finally reaches a program officer. So it's very complex and time-consuming in that RPAB, our Referral and Program Analysis branch, is classifying the branch, which is the scientific area, and we have 13 of them. They're also classifying the branch category code, which we have 257 of, and also program class code, which we have 84 of. And that corresponds to a program officer. So we're looking at a very complex, multi-level hierarchical classification problem. And not only this, but scientific areas of the branches can overlap in a lot of cases. So for example, childhood obesity is one of NICHD's mission areas. And while most of the basic and clinical studies of childhood obesity would be referred to the pediatric growth and nutrition branch, studies of childhood obesity at population level belong in a different branch entirely, and that's called the population dynamics branch. So we could see that there are a lot of challenges, and it's really important to understand the context and be able to really have SME knowledge to route these to appropriate branches and program officers. So handling the NICHD grant application involves several challenges, as I just alluded to. Our institute processes over 4,000 applications annually and determines their suitability for NICHD, identifies the appropriate branch, and also assigns the right program officer. So it requires a lot of time and a lot of accuracy because each application corresponds to a research project, and it's really important that it gets the proper attention and put in front of the right program officer. So our AI ML application referral system aims to streamline this process and automate the classification and referral tasks and ensure efficiency and reduce the workload on our subject matter experts. So we have a standard approach here that we've developed a combination of NLP methods and models to address this, very custom, along with our custom RPAB business rules mixed in there. So some key components include the data pre-processing, feature engineering, the development of the models, analyzing the evaluation metrics, and user acceptance testing with our team of experts. And there are a lot of benefits, like reduced manual errors, a lot of time saving, and just faster insights and a streamlined referral process. So onto the tech stack here. Our model development includes a combination of machine learning and AI techniques. So combination of AI ML models for classification, and the models are then refined with our RPAP-specific business rules and NLP methods. Special cases are handled separately, and we have different algorithms to handle those. And in the future, we may want to add a generative AI component to handle the especially challenging cases. And this modular systems architecture provides flexibility and scalability, so we can add and update models with ease. And it helps our system remain adaptable and responsive to emerging research areas. So another challenge is that research areas change over time, and that just adds another layer of complexity for these kinds of models. The modular structure also allows for reproducibility and the communication of metrics, transparency, and helps us ensure responsible AI practices are intact throughout the development process. So this is our current model prototype results and status. So we have a few models at this point. Currently, our random forest is doing pretty well, and we had notable success with about 85% average accuracy for our 13 branches. And if you look at that chart on the right here, you'll see that different branches there's variability with the F1 scores for the different branches. And this is partially due to the amount of data and the amount of applications that we have in our historic 5-year data set for the branches. And it's also partially attributed to what I was explaining about the overlapping scientific areas and the challenges that come with that. So we're pretty excited and continuing to develop, and our future development, we're adding in our business rules and further refining those, and working on additional models to find the one with the highest performance and swap that out accordingly. The expected ROI is impressive. So if we assume that our team is using the model's predictions for just 20% of applications, so if we have, we also print out the probabilities with each prediction, and if they're satisfied with those probabilities for 20% of the time, and they go with the prediction, then that's estimated to save 37 workdays per fiscal year for our team. So that's pretty exciting for just 20% of the time to use the model. And we strive to continue. And next I'll share, third part of this, so I'll share a framework and prototype demo of how to enhance the classification model like what I just showed with a Gen AI QA bot. So this is a next step for us in the future, and it helps address those challenging cases where we would like to add additional context and do more QA on the results that we get from the model, especially the lower confidence predictions. So whether using neural networks or random forests or any kind of classifier, we always encounter predictions with lower confidence, lower probabilities. And the theme and objective of this Gen AI-based QA bot is to review and refine uncertain outcomes and improve the model's reliability and trust. It provides the system with access to a larger knowledge base and additional feedback and can make the model more robust. I also like that here with the Gen AI QA bot added to the classifier model, we have the duality of deterministic and non-deterministic components. Because with the first step of more traditional AI ML classification model, be it neural network, random forest, SVM, anything, we have a baseline quantifiable metric of performance. And from there, we add this additional non-deterministic component. And I find that being in the public sector and navigating our AI ML policies, it's especially important to go step by step and begin with a more deterministic system as we have that baseline transparency and communication of the evaluation metrics. So the slide illustrates the architecture of this neural network classification system enhanced with Gen AI QA bot that I'll demo next. And it's designed to improve the accuracy of the model. And in the demo, again, I'll be using NIH reporter data of research projects, which is publicly available. And we will predict the appropriate institute or center this time for the project. So in the last model that I showed, that was predicting the branch that's within the institute or center. And for this model, I'm gonna take it a step up and predict one of the 27 institutes or centers for the research project that it receives, that it's doing inference on. So we start with looking at the flow here, start with data ingestion, pre-processing, and train the neural network, do your eval. And at this point, we establish a confidence threshold. So I chose 0.5. You can do thresholds appropriately for your use case, whether that's with a more standard metric like raw curve, or if you want to do a cost-benefit analysis, given that we will be sending data to large language model. So there's a time and cost component there. Once we set that threshold, then we can filter out the lower confidence predictions. So if the institute or center predicted had less than a value of 0.5 for the probability, then I flag that and send it to the Gen AI agent who has additional context on all the NIH institutes and centers, and it can make hopefully better prediction and send that back to the system. So we'll see this in action next. And yeah, for this I used 1 year of, or the most recent 15,000 funded projects were used to train the neural network. And this prototype Streamlit app, if I can play it, okay. It animates the behind the scenes process of what the Gen AI agent does when it sends a low confidence classification prediction to review. So again, the confidence threshold is set to 0.5. So you see, for this example, the neural network predicted the National Institute of General Medical Sciences for this research project, and the probability was 0.45. So that was flagged and routed to the Gen AI QA bot to review. And in the back end, we have GPT-4 that is prompted with a series of prompts that also instructs it to reason and produce its reasoning as to why it chose the institute or center that it does choose. So it's given the abstract title and research aims, and it has additional context of NIH institutes and centers. And like here, it predicted that the application belongs to the National Institute of Environmental Health Sciences, and it matched with the ground truth. So got that one right. The next example is an NICHD one. This is a tricky one. This is one that has overlapping scientific areas. So it had 0.4 for the probability of the institute that it predicted, and we sent it to the Gen AI QA bot, and it predicted correctly. And the last one, even lower for its probability, and also got that right. And if you saw the keynote this morning with the live demo, I'm not that bold, so this is all recorded. So that's the demo for the Gen AI QA bot. So to conclude, we've explored the application of generative AI in topic modeling, discussed the NIH RPAB AI ML referral prototype at NICHD, and showed the framework and future prototype for neural network classification with QA-bot. So generative AI can be embedded directly into established AI/ML frameworks and modernized decision science methods. We could use these NLP methods at NICHD RPAB for our referral and for our reporting. And these are just a few examples of many opportunities to use these kind of Gen AI agents within our traditional decision science methods. Some resources and references for packages. And that's all. Thank you so much for your attention.